Today we are talking about polynomial functions, and we want to be able to identify key features of polynomial functions, which we've already talked a little bit about already, so most of this should be pretty easy today. So, a polynomial function, this is a crazy way to write a polynomial function, okay? But a polynomial function is a function that is made up of coefficients and x2 powers, all right? So something like 4x cubed minus 2x plus 7, and a constant. So that's just an example of a polynomial function. So all the coefficients, so all the numbers in front are all lovely numbers, as long as they are not 0. And n is a positive integer. All the powers on x have to be nice positive integers, so positive whole numbers. We don't ever have any negative exponents if it's a polynomial function. And all polynomial functions are smooth curves. Hello? Hi. Yeah, sorry. Thanks, bye. The minute she calls. I'm like, oh yeah, okay. All right. So, they are smooth curves. So polynomial functions are smooth curves. Smooth curves, no breaks, no gaps, they are continuous. No discontinuities. They are smooth, gorgeous little things. I love them. I think they're so cool. And we can tell a ton about what a polynomial function looks like by simply knowing the degree. The degree of the polynomial is the highest power on x. And that degree tells us the basic shape, okay? It tells us a lot about what the arrows do. And we also classify our polynomials by their degree. And so here, I'm going to start here on, like, right here in the middle. We want to identify the degree and classify each polynomial function. So for instance, this one, here the degree is 2. And what shape is this guy? Quadratic, yeah, it's called quadratic. It is a parabola shape, okay, it's called a quadratic function. Let's go back up one. So what's the power on negative 3x plus 8? Yes, so that is a degree of 1. And what is that called? Linear, straight line linear, right? Linear is the name. And we know that that one is a slanty line. Well, this one is a downhill line, so that because of the negative slope. All right. This one's tricky. What's the degree of this function? 0. It's x to the power of 0. That's the sort of sneaky thing there. X to the power of 0, anything to a power of 0 is 1. All right, and so that really just goes away, and it just leaves the 2 behind. It has a degree of 0. Constant function, C-O-N-S-T-A-N-T. Constant function, that is a totally horizontal line. Hey, Thomas, can you move your computer so that I can see it, the screen? There you go, perfect, thank you, that's great. All right, and then here we have a degree of 3, the highest power is 3. And what do we call this? Cubic. And what do they look like? Yeah, it's the tall ones. This one's, so cubics go like uphill like that, or they go downhill like this, so depending, all right? And then here the degree is 4, and we call that quartic, yeah. And here we have a degree of 5, and we call it quintic, is right. We never say that. Usually we stop at cubic and we say just 4th degree, 5th degree, 6th degree. So we don't usually see quartics and quintics very often. So you can also reference it just by 4th degree, 5th degree, 6th degree, okay? So the degree tells us a lot. Now we talked about monomials yesterday, which would just be, hey, the one thing there, one term. Polynomials have all these extra little things added in, all right, many terms, okay? But they still have the same overall shape as their leader, okay? And the leader is the degree. If we know the degree of the function and the coefficient of the leading term, we can tell a lot about the function. We can tell a lot about the end behavior, which I don't want to go over again because we've already done this. So we have the same end behavior as we have in the past, and we get to tell just by simply looking at the power and the coefficient of the leading term. It tells us everything we need to know. So all these leaders, the leaders are the important things here. They tell us so much information. And so we're going to talk more about that. But we've already talked about end behavior, and I don't want to do it again. Yeah. So here we go. Using the leading term, give the end behavior of each polynomial function. So again, I don't like to memorize stuff. I'd rather say, hey, what does it look like? And go from there. So here we have, what's the degree of number 1? X to the 4th. All right, even or odd? Even. Okay, now the coefficient in front is negative. So what happens? Oh, arms down. All right, so this function goes something like this. And we know that just by looking at the lead term. Now, if you can make a quick sketch like that, then we can write our end behavior. As x approaches negative infinity, so as we move to the left arrow here, where is it pointing? Down. So f of x goes to negative infinity. As x approaches positive infinity, f of x approaches negative infinity. So that's the right arrow points down. So f of x goes to negative infinity. Beautiful. And that's all we need to know. If we can figure that out, we're good to go. So number 2, our leading term is negative 2x to the 5th. So the degree is 5. Even or odd? Odd. So the arms are odd. Okay? They're either like this or they're like this. Okay? Our leading term, the coefficient is negative 2. So is this a going uphill thing or is this a going downhill thing? Downhill, yeah. So this is going downhill. Odd arm starts high, goes low. All right? That's what the negative does. It makes it a decreasing function. All right, overall. So as x approaches negative infinity, so as we move to the left arrow, where is it pointing? Up to positive infinity. Yep. As x approaches positive infinity, what does our polynomial do? Negative. Goes down to negative infinity. So f of x approaches negative infinity. And this is all we have to do. Is it even arms or is it odd arms? That's all we're doing. Let's look at number 5. Number 5, our leading term is 1/2 x cubed. Is it even or odd? Odd. So we have odd arms. Is it the uphill arms or the downhill arms? Uphill arms, yep. Starts low because it is a positive leading coefficient. Those odd arms are ultimately going uphill from left to right, okay? All right, so as x approaches negative infinity, where is my function going? Down. Yep, left arrow goes down to negative infinity. As x approaches oh, that was negative infinity, positive infinity, f of x approaches positive infinity. It goes up. All right. You good? Yeah? Okay. Now, here's something kind of interesting. Describe both the power and the coefficient of the leading term of the polynomial given the shape of this graph. Interesting. What are you feeling about this one? First of all, describe both the power and the coefficient. The power and the coefficient are what we're looking for. It is an odd power. Very good. So it's definitely an odd degree. D-E-G-R-E-E. It's an odd degree. And is the coefficient positive or negative? Yeah, how do we know it's negative? Yeah, because it's going downhill overall. It is a decreasing sort of function. It has a negative coefficient. Okay. Do you think that this would be x to the third, x to the fifth, x to the seventh? Fifth? So, interesting, you can count 1, 2, 3, 4, 5. How many zeros does it have? So 5, it could be 5. Because that's how many times it crosses the axis. Yeah, interesting. All right, 8. Yeah, even or odd degree? Even degree. And it is positive coefficient because it's arms up. Positive coefficient. And you're right, if we had to pick, is it x squared, x to the fourth, x to the sixth? What are you thinking? So it's 4. You're right. It can't be, it has 2 real zeros, but it has so many turns, and the turns are important here. Yeah, so you can do that, and that's actually what we're going to talk about here, too. So you can see we have a minimum and a maximum and a minimum. So it has to be one more than those mins and maxes, at least. It's probably x to the fourth. So there are 3 turning points where it's well, here, we're going to talk about it right now. We're going to talk about it right now. Turning points, look at that. So before here we go. The points at which a polynomial function switches directions are called turning points. So here I'm going uphill, and I have a turning point where I go downhill, and I'm turning again. And so if the turning point is higher than any point nearby, it's called a relative maximum. So right here, this turning point would be called relative maximum. Relative maximum right there, that turning point where it changes, crests the hill, so to speak. That's the top of the hill, all right? If the turning point is lower than any nearby point, it's called a relative minimum. So this point right here at the bottom of the valley is called the relative minimum, okay? So we have a relative max and a relative min. Maximum and minimum values are called extrema. And these turning points help us figure out where a function is increasing or decreasing. So we have our increasing going uphill, we are decreasing, and then we are increasing on that next little interval, which we've talked about before, always. Okay, yeah, so the absolute or global maximum cannot actually happen on an odd polynomial like this one, because what is the absolute maximum here if this goes up? It's forever, infinity, right? So I actually can't have a global max, because infinity, we'd never really get there, would we? Yeah, no, not really. It has to be a number, and infinity is more like a theory, which is sort of hard. if you look and you count these turning points, so here's one turning point and then the second turning point. So this has two turning points. The degree is always one more, all right? So if there's two turning points, then the degree is third degree, all right? So that is one way to think about the degree. It's one higher. All right. Do I want to do this? I don't really want to do it. Well, we might as well. All right. So using the calculator. I think most of you already know how to use the calculator for this stuff. It is a required knowledge. We want to find the turning points for this function in the calculator. And so we're going to go to y equals. And I'm going to clear all that stuff out. I have x to the third power plus 5x's squared minus 8x's minus 1. And I'm going to do a zoom standard. So that was step one. Holy moly, look at that. Do I see all of my function? No, I don't. It is very handy to learn how to work the window of your function. And for most of this stuff in the calculator, you have to know how to change up the window. And I know that my function has a peak up here, and I need to be able to see the top of that peak. So I need my y-axis to be taller. So I'm going to go to my window. So go to the window, and I want my y maximum to be much taller. I'm going to say like 50. So I'm going to change my y maximum to 50. I don't need to change anything else. Everything else was fine. And then hit graph. There we go. Now I can see my peaks and my valleys, and that's important to see. Now, we want to find our relative maximum, which we know is right here. So we can do that by calculating the minimum and maximum. So we're going to go to the calculate menu, which is right above trace. So we're going to do second calc. And that's our calculate menu. And it tells us lots of good things. I want to find the maximum. So I'm going to click number 4. Are you all with me okay? Yeah? Do you all know how to do this? Yeah? Oh, okay. So there's Tinkerbell. Now, I'm going to use the left and right arrow keys. I'm going to move Tinkerbell to the maximum. And she's telling me I need a left boundary. So we're going to go left, 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 and hit enter, because I need to be left of the maximum. And then now Tinkerbell wants a right boundary. So I need to go back to the maximum and go right, 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 right a little bit, and hit enter. So that I'm giving Tinkerbell some boundaries to look between. So it's actually just going to look between these x values and calculate the highest y one. And now Tinkerbell wants a guess, so we go back to the maximum and hit enter. It's sort of left enter, right enter, maximum enter. And if it says the word maximum, then you know you did it right. So the relative maximum here is at negative 447. And then we're going to do the same process to find the relative minimum. So I have to go back to my calculate menu. So second calculate, now I want the minimum. So I'm going to move Tinkerbell. Move Tinkerbell to my minimum. And again, she wants to go left a little bit. So left, 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 enter. And now we got to go right past it a little bit and hit enter. Back to the minimum and hit enter. And again, you'll know you did it right if it says this is the minimum. This minimum is 0.666. Negative 3.81. I'll give it a 5. All right, I'll do 0.667. So I'm just going to tell you guys right now, because most of you are juniors, so you're going to have me next year. 3 decimal places. Always. All right. So 3 decimal places is great. 0.667 and negative 0.3185. And then if we have that, so I have my little picture of my curve here. My little curve was like this. Looks like that. All right? And we know that this maximum is right here, and that is the x value of -4. And this minimum is right here, and that's the x value of 0.667. So we want to know our increasing intervals and our decreasing intervals. We are increasing, going uphill, then we're decreasing, then we're increasing. So what is our increasing interval? -infinity to -4, union. .667 to positive infinity. Yeah. When we talk about intervals, those are intervals on the x-axis. We only care about the independent variable. So we are just talking about for the x values from -infinity all the way to 4 here, we're increasing. And from 0.667 all the way to infinity, we're increasing. And where are we decreasing? Yeah. From -4 to 0.667, we are decreasing. And again, that is x intervals. We only care about the independent variable. All right. How do you feel about that? That's pretty easy, yeah? Yeah, it is a super